Good morning. Good morning, everyone.
Good morning, sir.
So I've sent all the notes. Now I'd like to go through the cases. Which cases call for applications of circular motion? Applications of circular motion. Now, among them is vehicles negotiating bends on a horizontal path, also vehicles negotiating bend on an inclined road or on a banked road. And this is where we have cases of what we call toppling or overturning. So the first one is motion of a car around a circular level track. Motion of a car around a circular level track. That is, we have a case of overturning or toppling. Overturning is when the car somersaults, okay. Yeah. Now consider a car negotiating a bend on a level road or track for circular motion. The frictional forces F1 and F2 at the wheels provide the necessary centripetal force to keep the car in circular motion. Now, if this is the road, and this road has a car on it, these are the two tires of the car. Yeah? Idea the tires can be seen in this form. So if those are the tires of the car, we can have a normal reaction, R1 on the first tire, normal reaction, R2 on the second tire. Then the first tire can have a friction F1, the second tire can have a friction F2. But this car also has its weight, which is mg. Now, when the car is negotiating a bend, the tires are curved in that direction. Whereby if the car is to overturn, it overturns going this way. So what prevents it from overturning is the friction, F1 and F2. Yeah. So in that sense, you will see that the line, this is where the center of gravity is. The tires have a distance of A from the center of gravity, as shown in that diagram. Then the center of gravity can be at a height h. So with that knowledge, we can be able to talk about some of these conditions. Though that diagram there, the centripetal force was put in the wrong direction. It was supposed to be put this way. So this is where mv squared over r. Okay, I think it was put for only one reason, to confirm that F1 plus F2, the frictional forces overcome no force. So there is no force this way, to give us the resultant force, which is mass times acceleration, whereby F1 plus F2 would now be equal to mv squared over r as equation 1. When we predict that equation, we can also see that the reactions, if maybe this reaction was R, and this one R1 was S, therefore S plus R is also equal to mg. And also, if you look at these reactions of R1 and R2, you'll see that F1 is actually equal to mu S, while F2 will be equal to mu R. Or this can be F1 is equal to mu R1, then F2 is equal to mu R2. The reason why the react frictions, the mu are the same, it's because it is the same road. So the coefficient of friction is the same. It's the same road where the two tires are. So therefore, mu of S plus mu of R is going to be equal to mv squared out of R. And whereas S plus R, we have seen is already equal to mg, then we can merge these two and say mu into S plus R is actually equal to mv squared out of R. Then bring this one here, and we shall substitute mu mg is equal to mv squared out of R. We can lose the m, and then we can have v squared is equal to mu r g, and that's the final velocity. The velocity with which a body should negotiate a bend is mu r, mu small r g. Small r now is then, if this is the circular path, the distance from the circular path, from the center of that circular path is what we are calling what? Is what we are calling r. So mu small r g becomes the equation for velocity that predicts the velocity with which one has to slow down when negotiating a bend. That is why whoever is driving in a bend is what you call a corner or a turn. If the car reaches a turn, whoever is driving has to slow down. We call it negotiating. So when he's slowing down, he's negotiating the bend. Now, if the condition is to overturn, like I've said up here, overturning autopoding can come as a result of if V is very, very big, when the speed is very high, the car can easily overturn. I don't know whether you can see me here. Let me try to show you something. When you look at this, if this is your car, it was coming, it was supposed to turn like this. Now, when you come at a terrible speed, when you come at a very high speed, instead of the car turning this way, you will end up flapping the car outside, so the car can easily overturn and topple. So if the speed is very high, that is 1. If the radius is also very big, yeah. If also mu is very big. When mu is very big, it means the road is very. No, when mu is very small. When mu is very small, it means the road is very slippery. So if the road is slippery and you have a very high speed and you have a very sharp corner, then the car is likely to overturn. A very sharp corner means R is small. I think I've written this one wrongly. Should have been R is small here, not R is very big. So if R is very small, what does it predict? So those become the conditions for having what? For having overturning take place. Then furthermore, you can also take moments. Now that is just the aspect of doing what? That is just the aspect of proving that V is equal to mu RG. Now what if you go and take moments here at the center of gravity? What are you going to realize? When you take moments at G, we have seen the car looks like this. G is here. We saw this height was H. We saw this was SR, this was S. And then here you had what? The weight mg. But when you're here, this distance is A. Even this one is what? Is A. Then we have friction F1 and friction F. So you will see that when you are at the center of gravity, what is going to happen is the friction F1 is going to take a moment in that direction. F2 will also take a moment in that direction. RS will take a moment in that direction. I mean, S will take the direction which is clockwise. It is only R which is going to be anti-clockwise. But its perpendicular distance will be A. Even this one's perpendicular distance will be A, whereas the perpendicular distances for the frictions from the center of gravity for them, their perpendicular distance is H. That is why we could say F1 times H plus F2 times H plus S times A, they should give us the reaction RA. And from here, you could see that F1 plus F2 in terms of H is equal to R minus S in terms of A, the distance between the tires and the center of gravity. Then it is from here that you could also bring in, we had also seen F1 plus F2, what is it? F1 plus F2 was seen as mv squared over R. You can put it here and have mv squared over R times H is equal to R minus S times A. Then you can make R minus S the subject to give us mv squared H out of RA. This becomes equation 3 because you already have equation 1, equation 2, and equation 1. So I can imagine equation 2 and equation 3, whereby if I add them, where can I write this? I never wanted to eliminate anything. Let me use another color and write them here. Whereby you'll see that R minus S is equal to mv squared H over RA. Whereas R plus S is equal to mg. When you merge the two, you'll get 2R is equal to mv squared H plus mg over RA. Then you can see that the normal reaction is going to be equal to mv squared H plus mg RA over 2RA. Then if I want to find S, I subtract. When I subtract, I'll get mg minus mv squared h over RA is equal to 2s. Therefore, S will be equal to mg RA minus mv squared h, all is over RA. Now, this is where the physics is. You see, this was going towards the center. This is the center of this is the circular path. Where there is S is here on the second tire. And I've told you, if the car is to overturn, look at my power bank here. My second tire is inside where the car turns from. It is this finger. Now, if the car is to overturn as it tries to turn, it will topple out in this form. So it will get off the ground from the inside tire. So if the car gets off the ground from the inside tire, that means when S becomes greater, less than or equal to 0, then you will have mgRA minus mv squared h being less than or equal to 0. For that reason, GRA minus v squared h will be very less than 0. And therefore, we shall have this conclusion. Don't worry, all the derivations are there in the book. I'm just going through them in the notes. Then you'll have GRA is less than v squared h. So v squared will be greater than, okay, v squared, because this is less than 2b, GRA is less than over h is less than v squared. So it means v should always, if v is greater than GRA over h, then toppling will occur. That means you'll be driving at a very high speed. So if you drive at a very high speed, then also if the radius of the circular path is very small, and then if also the distance between the tires is very small, and also the height of the center of gravity is very high, then you are most likely to get a very big value of components which can end up making the car to overturn. So with that information, you can see that if I look at this next part, where are you? Yeah, so this is how these equations came about. So this first one, I derived it is already here, which I talked about here, which is this one. Yeah. Then if the speed is very high, the car slides. So, but for toppling, these are the conditions that you talk about these ones. But for sliding, you talk about this one. So sliding includes one, if mu is very small and G is and R is very small and the speed is high, the car will slide. Then here you get toppling and overturning. Toppling and overturning. When it is to overturn, I've told you if the car has a very high center of gravity, then it is easy to overturn. If the car has a radius R, which is very small, it is negotiating, it can also easily overturn. If it is speeding still, it also overturns. So here we only have two options, or three: speed, mu, and R for the car to slide. But here we have speed, we have R, we have the distance from the center, we have H. That is why, have you seen racing cars, Formula 1? Those cars, they are designed in a way that they have a wide base. The distance between the tires is very long. The tires are almost outside the car. Why? They are lowering the center of gravity of the car and increasing the radius between the center of gravity and the edge of the tires. By that, the car is more comfortable to negotiate a turn. That is why lorries, which are having a high center of gravity, buses, they cannot easily overturn a sharp bend, whereas small cars can, because for them their height is low, so their center of gravity is lower. So those cars or vehicles which have a low center of gravity, they are more stable on the ground, they can easily negotiate bends. That is why most of the racing cars are those kinds of cars which are low down, yeah, they are not raised up. That's why even you can't even still find a pickup racing, it's hard. Fine pickup racing with the saloon cars, these small cars, no. If they are small cars, they are small cars. If they are pickups, they are pickups. Unless someone has a question. Someone has a question, please, and please ask if I can move to the next item. No questions. We have case 2. And case 2 says, when we have motion on an inclined plane, and I told you this motion on an inclined plane is what we call a banked road. So motion of a car around a banked inclined track. Now, in this sense, banking of a track refers to the designing of a track around a corner or a bend in such a way that one edge is raised over another linear edge. They can ask you to define banking. What is banking? So the definition for banking is there. Or they can say, what is a banked road? A banked road is part of a road where one side is raised over the other. Yeah. For example, one road can be like this, then the other part is raised over. So if the other part is raised, the car is moving along this track. Now this car is trying to negotiate a bend on this inclined what? Inclined road. What are the conditions? So consider a car of mass M negotiating a bend of radius small r. And if this car is negotiating a bend of radius small r, what is going to happen? It is inclined at an angle theta to the horizontal. It is assumed that there is a tendency to slip at the wheels. That is, the wheels there can be a tendency for the car to slide, but there is no skidding. Therefore, no friction force exists. If we assume there is, if that is, because one thing people should know, these conditions of saying that sometimes I don't talk about the condition of no friction because there is no road which is slippery. The only parts where roads become slippery is when it has rained and the water makes the road slippery. But some questions can be set, like, for example, explain why a fast-moving car runs faster on Maram Road than on Tarmac Road. I think all of us know Maram. Maram is the soil. The soil, most of the thingy runs very fast. I mean, the Maram Road has some stones on top. So those stones make the road become slippery. So if the road has been made to become slippery, there is less friction on Maram roads than on Tarmac roads. So the car running on a Maram road overcomes less resistance on the road than a car which is moving on a Tarmac road. A Tarmac road is the black road, the Corans road, which we use for cars to take us to school, to homes, to villages. And then the Maram roads are those home village roads you have around, those small roads which are not tarmac. But if you're driving at 20 kilometers per hour on a Maram road, you see the car is running faster. Yet when you come to Tarmac road, the car goes slowly. It's because the Tarmac road has a very high coefficient of friction, hence it has a high frictional force. Whereas the Maram road has a lot of slipperiness on it, and that means it has less friction. And for that reason, we have minimum resistance. But what I wanted to show you is that there is no road without what? Without friction. So this condition is just talked about here, but the condition for having a road without friction, practically it is not there. But we just wanted to talk about it in this definition. So if you just talk about it, then you might have a car on an inclined road or on a banked road with its tires. Now, if this car has its weight as usual, The rod is inclined at an angle theta. Then along this line of the horizontal, we shall have components of the normal reaction from the tires. For example, if the tire, you have this one has a reaction R1, then this one has a reaction R2. When you resolve, you'll see that if this reaction, because reactions act at 90 to the surface, and yet this was theta. So we need to resolve the reaction to the horizontal. If this is theta, then this is 90 minus theta. So R cos of 90 minus theta, you'll get R1 plus R2. Both of them will face the same direction, but with sine of theta. Then this is the direction towards the center. Because what happens is, he's trying to, when you see these notes, when they put this mv squared this side, they are trying to show you that the mv squared is equal to this one. But ideally, from mechanics, that makes it be in equilibrium, which means this force is equal to the other force. But the original, the concept which is actually appropriate is that horizontally, there is no component of force this side. And now if there is no component of force this side, this car is trying to negotiate a bend in this form along an inclined what? Road. So towards the center is this side. And if that is the side towards the center, then R1 plus R2 sine of theta, they overcome no force to give us the resultant force, which still comes to the same thing. But what I fear there is learners may cram that always the centripetal force is equal to the component of M of R sine of the reaction at the tires. But yet the definition is actually that these components, they overcome no force to give us the resultant force, which is mv squared over R. But otherwise, if you say mv squared is equal to that component, it's like the way we say R is equal to mg. When you say R is equal to mg, these are action and reaction forces. But yet these ones are not action and reaction forces. They are one is the resultant of the other, which comes as a result of the algebraic sum of forces acting on the system. Sometimes you'll find some books having split them into R1 sine of theta plus R2 sine of theta is equal to mv squared over R. They are all talking about the same thing. But you as physics students, as 5-star students, taught by 5-star teachers, do you understand the mechanics behind here? Is it just this is equal to that, or this is resultant force? You should know that this is always resultant force in circular motion. Why? Because the centripetal acceleration is the v squared out of R, which is actually the ratio of v squared over R in terms of acceleration. Then also you have to resolve these R1 and R2 to the vertical. When you resolve them to the vertical, the angle here, this is now mg, the angle here is actually theta. So you'll get R1 cosine of theta plus R2 cosine of theta is also equal to mg. Then from here you'll get R1 plus R2 into brackets cosine of theta is equal to mg. If this is equation 1 and this is equation 2, that is if there is no tendency to slip or to skid, then ratio 1 divided by ratio 2, you will get R1 plus R2 of sine theta, all is over R1 plus R2 of cos theta, which is equal to mv squared over R divided by mg. When you lose this mg and lose this with that, you get tan of theta is equal to v squared over rg. Do you realize that this equation reduces to v squared is equal to rg tan of theta? And that equation is familiar to you in conical pendulums for horizontal circles, because the circle will be horizontal as it tends towards that side. So this is the condition for horizontal circles. So it can still be derived even if the vehicle is moving on an inclined road. And have it in mind, all these questions can be derived. I mean, these questions can be asked to derive. This is physics. In mathematics, they cannot ask you to derive. Okay, they can ask you to show this in a conical pendulum. But in physics, when they ask a question, 3 marks and above, you derive and substitute. So we have to have that also in mind. So this is the analysis of the angles. This one here. Like I said, this is at 90. This is Z angle theta. This is 90 minus theta. Then also balance up here will be theta. So as you take R to the vertical, you compress R. As you move away from the angle, you come and compress 90 minus theta, which is sine. So that is how we come up with these equations. Okay, any questions also there? Like I said, if some people miss some of these parts, we can come and borrow them and you don't understand what we are getting or how we are getting them. So I'm seeing even here, people have refused to attend the class, but I have no option. I have to go on. So that when you have risks of sitting, you will appreciate and say, teacher was there for us. He made it a point that we get the topics as early as possible, but we disappointed ourselves. I need people to say that to themselves when they have failed to make it. But those who will make it, they'll definitely say, yeah, the teachers played their role. We were there. We did not miss. We put in a lot of energy. And here we are. See, the derivation is there. Then there is going to come another case when there is frictional force. When there is frictional force, but like I've told you that previous example, derivation, in real life it doesn't exist. We don't have a road without what? Friction. Now, what if a car is negotiating a bend and it wants to run very fast? When it is making a turn very fast on a circular bank, as it tries to run very fast, it will fall out in this direction. And it can only fall out in that direction if the reaction on this tire, R1, is 0. So if this is towards the center, remember it has its component of its weight here, mg, and this is theta. Then what prevents it from falling upwards? Is the friction on the tires F1 and F2, which frictions can also be analyzed from this line, whereby you can have, if this is the reaction, R, remember I told you it's supposed to be at 90, then we have the weight mg. Then if you have the weight mg, this would be theta, and this would be theta. Then this is, remember, if this is theta up here, so 1, we are having now friction down here. So this side we shall have friction cos of theta plus r sine of theta, overcoming nothing to give us the resultant force. So horizontally, F1 cos of theta plus F2 cos of theta plus R1 sine of theta plus R2 sine of theta overcomes 0 to give us mv squared over R. We can also have R1 plus R2 as the total reaction, R, and F1 plus F2 as the total frictional force, F. Okay? In that sense, we shall have F1 plus F2 of cosine of theta plus R1 plus R2 of sine of theta is equal to mv squared over R. Then you will have F cos theta plus R sine of theta is equal to mv squared over R. Now vertically, look here. Vertically, you will have R cos theta. Then this F can be resolved downwards and have F sine of theta. So therefore, F sine of theta, the total friction, plus the weight mg. These ones are counterbalancing forces. So straight away I can say is equal to R cos theta. It is from here that I can say that mg is actually equal to R cos of theta minus friction sine of theta. So this becomes our equation 1. This can become our equation 2. Then I can divide Roman 1 with Roman 2, and I'll get F cosine of theta plus R sine of theta is equal to mv squared out of R. So this is R cos of theta minus F sine of theta divided by mg divided by this side. When you divide everything by cos theta, we shall get F plus R tan of theta all over R minus friction tan of theta is equal to V squared over RG. But remember, friction is mu what? Is mu R. So furthermore, we can substitute. Let me wrap this part. Furthermore, we can substitute and reduce that function in terms from F and R to something in terms of mu and R. So therefore, what shall we have? We shall have, so those who are not attending these things, you cannot understand them. You know, they know what they will do, they will see what they will do, how they will interpret the notes. I'm seeing they can't understand. It is not so obvious. Over R minus mu R tan of theta is equal to V squared out of RG. Vamush the R throughout. Therefore, V squared is equal to mu plus tan of theta, or is over 1 minus mu tan of theta. Then the whole of this can be multiplied by RG, whereby finally the velocity is the square root of mu plus tan of theta, or is over 1 minus mu tan of theta times RG is the expression for the car to overturn, as if it wants to overturn upwards. Then if it wants to overturn downwards, that one you're going to derive it, you just reverse. Reverse the friction, overturning downwards. You reverse the, you're going to derive, you derive it for me actually right now, so that I see whether people were following. We are overturning downwards, and if you're overturning downwards, there is a tendency of friction acting upwards. F1 up, F2 up, reaction R2, reaction R1. More also of these derivations are in understanding mechanics and Roger Moncaster. So please, can you go ahead and prove for me the equation for velocity when the car tends to overturn downwards, as I've derived when the car tries to overturn upwards. But if someone has a question, please do ask. Please try to derive. And now the other thing also, these diagrams, you sketch them with a ruler. You don't just draw forces without a ruler, both in physics and mathematics. The forces must be drawn with a ruler. Someone with an answer? The people just disappeared, some of them. Anyone with that answer? Yes, I was saying, in case people have failed to prove, this was the proof I was asking for. Now I can't proceed any further because people are very few, and if I ever proceed, it is still me asking myself to be answered or answerable to your questions again if you get challenges. So as people get challenges, let me minimize my questions. I will not teach a lot, but I intend that if you have a group of at least 20 people, they can teach for 2 hours. I had wanted to teach for 2 hours, but I've failed. And people should know that I'm sacrificing, because right now I'm in Kabale for my tournament. I came with the volleyball players, my team, but I have sacrificed and they're in a technical meeting and I'm here teaching. So if I'm here teaching and people are not attending, and yet it's not me who is benefiting. There is that aspect. I don't know that people know that they are the ones benefiting. So, okay, let us stop here. But in case of any other questions, please inbox me. Those who are going to start looking at numbers, no problem, as you wait for me also to come next time and do numbers. Okay, can have a nice weekend.
Have a nice weekend too.